Hi, everyone. Welcome. Just give me a second to share, and then we can get going. Hopefully, you can see my slides now.
Yes.
Welcome, everyone. Good morning. So I'm Doddapaneni. So I lead a team that develops many of the profiling tools that you may have used, or we'll cover some of them today. If you haven't used them, we'll give you an overview. Most importantly, I'm trying to, in this talk, so I want to give my perspective about how we develop a very wide range of analysis, profiling tools, monitoring and analysis tools. And it's kind of difficult to understand how they all complement each other, and also how you can benefit by finding the right tool to use it for the right job. And so that'll be the main focus, rather than a lot of the specifics about each tool. So I'm trying to figure out how to tie them together. And this may be a perspective that you don't often hear. And so that's what I would like to offer today. Okay, my screen sharing seems to be done. Okay, so with that, let me dive into it. Okay, so for today, the agenda goes something like this. So I'll first give you a overall, what's the big picture view of the developer software, and how the analysis tools fit in that. And then I also want to introduce you to one API, if this is something you have already heard. So it may be simply a reiteration of the overview. If not, so it's something that will probably help you navigate as you hear about it, what's changing, what's not changing. So I'll give some perspective and then link the analysis tools into this one API. And then we'll do a bit of a deeper dive into, so what does it mean to do performance engineering, and how the tools that we offer fit into it. And some of this is actually not relevant, even just specific to our analysis tools. It could be even any other your preferred tools, but it's a little bit more an outlook in terms of how I view the role of the performance tools and performance engineering in the software development lifecycle, and then conclude, and then have some time to answer your questions. So with that, but I also want to give you something, as Yuri has mentioned, you're welcome to submit your questions as we go. And this being a virtual forum, so we'll try our best to be making it a bit more back and forth and interactive. But so I have a colleague of mine who's monitoring it, and he will chime in as needed to relay your questions or ask your questions on your behalf. So yeah, let's try keeping it a dialogue where it makes sense, or if there are some clarifying things, we'll handle them as we go. So the big picture, so what's Vtune Profiler? So some of you already know it, and others you don't know. We'll give you an overview on that. And then, but really, so what's the big deal about, right? It's just a profiling tool. And but what I will hopefully convey to you is that it's a special kind of profiling tool. And there are lots of things that you may not know you can do in terms of gaining insight into performance and how performance varies based on the hardware. Vtune is an essential tool. You must have it if that's your goal, where you're tuning to get the most out of a hardware platform. From a software perspective, it'll give you really that insight, linking the performance insights from the hardware monitor data back to your software. So then we'll also talk about, you may have heard about one API. If you haven't, you will today. And then how does that, so whatever tools that you know today from Intel, how are they changing? What is not changing? Also, just quickly reiterate that these tools are also part of the larger developer software offering that called the studios. And then we'll give you some examples of the specific Vtune usages, especially focusing a little bit on the newer features and some of the developer experience and productivity features we are adding. So now to this is basically what's the motivation for one API, right? So basically, as we see it, the application workloads are becoming more specialized. So especially with the vision, AI, and autonomous driving and various other kind of things, it's becoming very domain specific, very specialized, and then hardware is also getting specialized to accelerate those workloads. Either it be GPUs or could be other kind of accelerators that are domain specific or are more field programmable devices like FPGAs. So what's the challenge if you're a software developer, you're looking at all of this one. So your challenge is there is a diverse set of programming languages. They're not depending on your specific workload or specific device or type of architecture you're targeting. They vary, and so you have to navigate all of that. And also in terms of any libraries, frameworks, there aren't consistent API to basically be able to get your compute done on this diverse set of compute architectures at the bottom. And then the tool support itself is inconsistent. So I think one of the big challenges that we heard from the ISV community and software developer community at large is basically, I have to repeat my investment or my project. The cost for us is becoming, we have to specialize for each variant, and ideally they like to keep the effort as much shared so that you don't have to really double every time you're adding a very different architecture to target. So then what is one API? How does one API solve this, right? So at a conceptual, at a very high level, one API is both an industry initiative, so meaning that it is a specification that anybody can implement. So we in fact have encouraged the other hardware vendors and software vendors that offer frameworks and libraries and hardware to be able to implement to the spec. So from that perspective, it's an open spec. We publish it and managing it through an industry advisory board. And then we also back it up with making a set of tools, essentially enhancing our industry-leading compilers, libraries, and debuggers and analysis tools into our Intel product. So you'll see sometimes it's used in both contexts, and they both are valid. So what is this program? So essentially, one API is, you can think of it as a data parallel programming model, or basically where the parallelism is much more explicit and easy, so that we can really be able to target essentially the compilers, libraries, and the tools can take the expression of the parallelism that is intended by the developer coder and be able to actually map it or fully utilize, say, for example, in the GPU, you have a large number of execution units, and so you could really, to be able to fully utilize it, you need a new programming model where the parallelism is much more explicit, but also it's very intentionally described. So if you're familiar with SQL or OpenCL, I think this is, we are even taking it further. So essentially, the data parallel C++ programming language that we offer is basically running faster than the industry standard, and we hope will become standard, right? So we are driving that back into the standards. And then you will also see that it is interoperable with the existing HPC programming languages. So now we are talking about the one API product, and then in one API product, you basically have so for direct programming, you have a C++, a derived language, data parallel C++ for direct programming to the your algorithms. But also in a lot of cases, when you have rich set of libraries similar to the MKL that we have for, or AI acceleration libraries like and analytics libraries that we have. Those will be able to target to the XPUs that you see down below. So that means where you see an API or a library function that captures what you're trying to do, you will be able to use that. And then where you need it to express directly, you'll have direct programming. So that's not much different than what you do for CPU today, but so I think the same way of using a rich set of APIs combined with a very productive programming language. Now you can really cover the spectrum of the cross or diverse set of compute accelerators down below. And then analysis tools that you're familiar with, so the Vtune Profiler, Intel Advisor, Inspector, they also will support the data parallel C++ and work with a data parallel C++ APIs in the libraries, but also the OpenMP programming model that you are familiar with for some of the HPC developers, they will also be extended for offload to accelerators, especially the GPU.
Sri?
Yeah.
One question for you from the audience is whether you think one API can deliver performance that is better than an experienced programmer for the specific domain, for example, CPU, GPU, FPGA, and others.
I think the right way to the way I think about it is, let me be clear. So are they asking more like, I already have a high performance C++ code, would I be able to get anything more better than that by switching to data parallel C++?
That's the way I understand the question. Assuming you already have the specialized knowledge to program to those accelerators, would you get additional performance benefit by using one API?
So I think you would. In general, we found that the OpenCL stack is not very is not as mature. So basically, what we are doing is putting a lot of performance engineering into the runtimes and into the compilers. So I think by simply being able to write on top of that, I think you would get some benefit. You still will need to bring your expertise in terms of how to write a performant code. Is still an obligation on the developer. So I think all the tricks that you know how to do, there'll still be things you want to bring when you move to the data parallel C++, but you get a lot of the benefit of having a robust and performant runtime compilers, libraries, and then tools to debug, etc. So I think that's the benefit you'll get. Other thing is, if once you have a performant code on one accelerator, your path to going to the next one hopefully is not double the effort, right? So because you will need to do some additional amount of tricks probably based on a different accelerator, but you would be able to leverage because it's a single source code. That's another thing. You don't need to really duplicate for every accelerator. Hopefully that
I think that answered the question, and we got another one with regard to the one API tools and toolkits. If you can comment which of them are going to be open sourced versus closed source.
I don't have it on top of my thing, but most things, if you go to, I think it's oneapi.org or com is the initiative. There you see the specs and also a lot of links to the open source. So a lot of our, some of the libraries and compiler are open source. Analysis tools are not, debugger is not. So I think in general, most of the libraries and compiler are open source.
We will add those links to the presentation.
So next, I wanted to comment quickly, remind people, if you if you have been using Vtune or any of the analysis tools from Intel that come with the Parallel Studio, or some of you may have a System Studio packages that you use, those are already included in there, and so essentially, in the future with the one API, we are in the beta right now, and they will so essentially when we launch the product version of the one API supported developer tools, you will see them also included. So just stay tuned for that in terms of the product offerings that support one API. At the moment, one API enabled features in the tools are under beta testing, and you're welcome to join if you haven't already joined and test drive them. And then if you want to know more about the analyzers, and so just here are the links at the bottom of each of these boxes. You can just go find a lot of useful information. There is training material, cookbooks, videos, case studies, customer codes. So whatever you're looking for, and also a link to download the software. And analyzers are free to download and use for commercial purpose. And so this is something we have changed last year. But if you desire a full support from us in terms of being able to handle your bug reports and other things on these things, then we also offer commercial license. So that concludes basically just the quick glance at the one API and the high level stuff and the big picture. If there are any other questions that's up, I can handle them now on the previous section, or can handle at the end. Now I'm going to transition to really talking about performance and how the analysis tools fit into the performance engineering that you guys have to do.
There are no pending questions, and you're good to go.
Okay. So with that, let's dive in, right? So before getting into the specifics, basically, maybe I'll take a little bit of a historical perspective and then talk a little bit about, I think maybe if you go, maybe some of you may remember, and Vtune has been in been a product for a very long time. I think it goes back to almost 20 years or so, more than 20 years. And so if you'd known it a decade ago, it might have been like a unique tool, but it is also more of a one kind of a tool. It's not a comprehensive profiler. It mainly did well on the CPU side, didn't really do much for either the memory or the IO or storage or those aspects. And also, even when it did the performance, it really looked at it from hardware-based and really didn't do some of the software and stack-based, some of the software context profiling that we do since then. So I think some people may have that view that they looked at it in the past and say it's a hammer, and well, I don't have nails, but so maybe for us it used to look like everything is a nail because we had just that tool. But now what I wanted to say is, so even though it's not a secret, we haven't been hiding it, but it's been hard to get that message or change the mindset because there is a lot that's changing, and it's changing gradually. So it's kind of hard for people to perceive. So it's kind of become a secret that what we have is not really a one tool. Really what you have is a toolbox. So even Vtune packs a number of analysis tools or capabilities, features, whatever you call them. We call them analysis types within the product. And they have been evolving as we innovate and introduce new analysis types. We also find that the number of analysis types are increasing, and so the complexity that you as a user need to deal with is also increasing. So we then try and combine them, make it more tractable for you. So that is an ongoing journey, and we have done quite a bit of that. But we are also realizing that that in itself is not sufficient. And so we are now contemplating how to actually do more things automatically if you desire not to be really controlling and manually driving what analysis and how much you do. we want to be able to mostly benefit from knowing your application, and then that knowledge, because you may have done analysis a number of times with that application or a workload, and you don't necessarily need to keep repeating, and Vtune can remember that knowledge. That's a feature focus we are, and I'll talk a little bit at the very end. So that's one, and then we have been we have been extending to cover the entire server platform or the client platform, as well as for the different segments like embedded, storage, networking, persistent memory, and so you'll see some of that. And then we have also been working on other tools like SockWatch, which is more power energy focused. Primarily started with a battery life analysis for the laptops and small form factor things like tablets and phones in the past, and now we are finding that energy and power is also very important thing as you optimize on the servers, especially thermals and energy consumption is also a limiter in terms of how dense you can pack the hardware configurations and how much throughput you can get per form factor or per watt. And then Advisor Inspector are things you'll realize. So Advisor is a tool we created when we were pushing towards multi-core, and then of course, on the server, many of the codes were threaded even then, but on the client, they weren't. So we needed some tools to help a lot of the broader software industry to start to introduce threaded parallelism into there. And then we soon realized that it's not sufficient to do threaded parallelism. There is also vector processing units, and so you needed to take advantage of it. So we extended Advisor for vector processing. And now we are on to offload to accelerators and things like that. So I'll talk about that. And then GPA, I'm really not going to talk much about it, but I just want to mention that if you are into using our GPUs to implement PC games, computer games, then we have a graphics performance analyzer that helps you to understand how to optimize and get the best frame rate on our GPUs, Intel GPUs. So now switching to a little bit about, so what does it mean to, so we said a performance deep dive, and so before we go into tools, what is performance made up of, right? Of course, if you are looking at your own code, it will be hard to understand how does actually this perform. I think with the modern computer hardware and platforms, it's pretty hard to actually look at the code, even for an expert in that domain, to really understand what the performance profile for it looks like on a given hardware configuration or on a given CPU architecture. Because there are so many issues, right? So one, you need how well is this code going to get translated into compiled by the tool chain, and so how will it how efficient it's going to be within the CPU pipeline core, right? So basically, your superscalar architecture, how well do you utilize it? That in itself is very challenging, but then it doesn't stop there. So with now the superscalar architecture is also going more vector, then you also want to know is how much more can I do? Because pretty much you can do all of the compute in a vector form, your loads and stores can be vector form, but also loads and stores can be pipelined, and so it's hard to understand. And then minimizing wasted cycles, right? So basically at the end of the day, the performance is, if you can't keep all of your processing units busy, then you have stalls. That may be because things don't get to the processing unit's CPU in time from caches or memory, but also sometimes it's coming from the network or from the storage. And then when you do all of that, CPU itself is highly parallel with many cores, and then you with hierarchical memory or more NUMA nature of the memory hierarchy within the platform, it's also that you needed to harness some process parallelism, and I'm not even talking about distributed here. So just even this itself is complex enough, and then some of you will have to deal with distributing it over on a cluster. So then developers themselves, right, so they specialize, right? So there are coders who may be coding algorithms or are in their specific module and may not be seeing the full picture. And then you have software architects and integrators, and so who are really worrying about how to integrate all of these pieces into an application or a software stack. And then you have performance engineers that are kind of straddling both the hardware and software. And I'm trying to understand how to make all of this either a single application or a bag of workloads really deliver the optimal performance. So now, why do I talk about the developer roles? I just wanted to kind of show you that you may not be all of this, right? But you may be one of these roles, or sometimes you actually play some of these roles during the life cycle of a project. You may be a programmer, also you're an architect. You may also be doing, so I'm not saying if there is you're only one of these roles, but each has different demands in terms of how tools need to be utilized. So with that, so what I wanted to really is conceptualize basically think of these as building blocks in terms of workflows. They are modularized, but the real world is a bit more complex. But I think it's still useful to think of them in this modular fashion. So think of the design flow, right? So the design flow here is code design. So, and when I really talk about code design here, not so much algorithmic design, but more like this software programming model kind of things like threading model, vectorization model, or offloading to accelerators. And also I have a very graph-oriented way of describing my compute. And so there is a flow graph is the kind of model that many of the domain-specific people are using for some time now. And also with AI, it is a good match. So now if you're doing one of these things, what do you do? So you can say, I have an existing software, which may not be threaded or may be threaded, but may not be vectorized, things like that in any order. And so what you can do is pick a thread and say, I would like, it's threaded, but it is not at the level that I want it to be threaded because I need more thread parallelism in my code to fully utilize the hardware I'm targeting. And then what you do go through is a workflow we will illustrate in Advisor that will, you can actually start analyzing and saying, is there opportunity to increase more threaded parallelism in the code? If I have to do it, what kind of a code refactoring or code changes I need to do? And in the end, will they be profitable? So you can do a lot of that modeling and then iterate it. And then when you're iterating it, at some point, you may want to say, hey, let me do a quick profile using my profiling tool, like, for example, Vtune, and then see if things are okay. And then you can come back and do some more design work. So then you have a profiling workflow, which is, again, you can start with and say, since performance itself is many things, and they actually matter both at the design stage and at the tuning stage. And so, but this is the tuning stage or optimization stage flow. So what you're doing is, in the past, you would directly jump in and say, I want to optimize my code using Vtune or some other profiling tool of my choice, and then you start profiling and then understanding where the bottlenecks. What we're finding out is a lot of the feedback we've gotten over the last several years is, hey, life is very challenging, and I don't have time, and I don't want to spend a few days or even a few hours to figure out if I needed to even tune. So we needed another mechanism to understand, is there a triage stage where I just need a quick assessment, a snapshot, a performance snapshot of my application to understand, am I missing some performance I could obtain if I tune? And also the triage will tell you a little bit about what are some of the things that I'm missing, right? So that way I can figure out what is my starting point. So when I go into the profiling stage. And then the configuration workflow, this is a little bit of you can say a fork. You do the design that's mostly for software developer, and you have an optimization flow, which is also for software developer. But configuration workflow can be for either an infrastructure or a hard system engineer, or could be your application performance engineer who is looking at it and saying, I also want to figure out what is best hardware configuration I can put together for my particular application or workload. So what will deliver the best performance or best ROI for my customers and things like that. And it's very common, right? So some of the high performance applications like databases and enterprise resource planning software, they also recommend and say, so to run best for this kind of performance profile, you needed this kind of hardware, and so they recommend really what the size, so how much, what CPU to have, and how much memory to have, how much storage to have, etc. So they'll give you basically a reference spec for the servers that you need to run on. But if you are really trying to optimize that, and then you have an in-house workload, or you have actually for your own custom need where you're mixing multiple different servers onto the same, you can do this through our tools. Okay, now I'm going to go a little bit into the design workflow, and I think I got about 25 minutes, and I want to leave about 10 minutes for Q&A, so it's about 15 minutes. So I may be rushing through a little bit, but I'm okay to skip some material. These files will be published post the summit, so you can browse through them, and you can also, it has links, and you can get back to us or learn more getting online. Following the links. So the advisor, basically the concept with the advisor is essentially you design it. So by designing it, basically you model it, and then you basically can tune it, and then you can also, when you model it, you can also model and say, so take for example, I think the next one I have the why modernize, basically. So think of it, Dave, if you have a serial code, this is what you get on a modern hardware, right? So this goes back a little bit to old data, but I think the picture would be even more stark with the newer architectures. But if you only vectorized, you get only a little benefit. You only threaded, you get a little bit. But if you did both, you are getting a huge benefit, right? In this particular example, we were showing 130 times the serial version. That's the power of this multiplicative effect that you would see by really paying attention to all the performance vectors. So here is a quick quote about what people say about it, so the kudos that we get. Okay, so automatic vectorization often is, so what you may ask, right? So I think if some of you are familiar, we have been telling you also that Intel compiler is the best at auto vectorization, so please use it and benefit. But what we found is that it's great. It does the best job in the industry, and it in fact gives you a lot of, it's for free, right? So the performance you're getting by turning on auto vectorization is something that you're able to get without much effort. But there is also a limit to it, because oftentimes the compiler cannot discern by certain dependencies or other things, and so as a result, it has to make conservative assumptions, and that misses, that certain loops don't get vectorized. But also sometimes it makes an assumption that by vectorizing something is beneficial, but it's based on static modeling. Whereas using the advisor, you're able to also dynamically profile and then actually compare what the static prediction is and what's the dynamic performance for that particular vectorized loop. And so by looking at it, sometimes you can say that, hey, this wasn't actually a winner. In fact, the vectorized one is running slower than the serial one, right, unvectorized version. And the reasons, there are some good reasons why that happens sometimes, because either you are memory bound and you really don't have as much effective vectorization you could do on a given hardware. Other times it's simply that you have masking because there are dependencies, and so you're really not doing vector, full vector, right, using all the slots lanes in the vector lanes. So what we found is it's really a hybrid feature. We are not saying either or. So you use Intel compiler. It gives you a very good diagnostics, and we pull the diagnostics into Advisor and let you then prioritize which loops are more beneficial in terms of overall performance speed up to the application. And if the vectorization compiler was able to handle it well, and it is in fact proven in dynamic profile that the benefit is commensurate with what is predicted. And in cases where the compiler was not able to vectorize, the advisor can give additional things saying that if you do some code changes this way, you may be able to do it similar to how we do it for threading. So I think I can probably skip this in the interest of time. And then there is another one I want to give you guys. So for some people who are very much high performance kind of code, not necessarily in the scientific domain only, but in lots of areas where you have a lot of number crunching and you have intense compute loops. What the roofline analysis in Advisor does is actually tell you on a given hardware, what are your bounding? Are you fully utilizing it? Are you at the peak that is possible? So basically, we look at it in terms of how much compute you can do per iteration versus how much data you have to fetch from caches or memory. And then you draw basically based on what the hardware can deliver in terms of the effective throughput from the different cache and memory tiers, plus the amount of ops that could be effectively performed. There is a sweet spot, right? So if you have these dots that keep showing that they are below the roof, that means that there is an opportunity to further optimize this loop. But if you're already near the ceiling, then there is no point in further optimizing because that hardware will not deliver anything more than that, right? So even though it may look nice when you look at the code that you are able to further optimize it, but it is an optimization that's not warranted. So, and this actually is a very popular tool. We introduced it a few years ago and has a huge traction among the HPC customers and now also finding it in the AI domain. And then I just want to quickly say that as we talked about one API, we are also trying to help you to essentially analyze your profile on the CPU, on the Xeon platform, and then be able to actually mark up and tell you, hey, you could offload this particular loop nest or this particular parallel region, and then if you do it to this particular version of the GPU, or you can get this much benefit. And that takes into some modeling of basically how much compute we could do in parallel on the GPU for that particular loop, as well as what's the overhead of transferring the data, shuttling the data between the CPU main memory into the GPU memories and back. And so sometimes that helps you to essentially get the first approximation. So essentially our model can be somewhat approximate. It's not precise, but it is good enough for you to be able to make that choice, because we can get somewhere around 70–80% accuracy in terms of what the actual benefit you may get in the end. And that's a good enough approximation for you to make that before investing a lot of code refactoring to actually implement the acceleration of that particular loop by offloading it. And then again, we also extend the roof line to the GPUs and the GPU memory hierarchy. And this is all available in the beta versions of our tools today. So now with that, I'm going to switch to the profiling workflow. And here I'm going to be a little bit briefer. There are a couple of more talks later on in this today. They will go into more depth on Vtune, and especially as it applies to developing for persistent memory and storage. So that's part of the motivation why I'm going to keep it a little briefer. But I also wanted to just talk about, people are not familiar with probably snapshots, and because we haven't fully integrated into our workflows within Vtune, so sometimes it's harder to discover it, but this is something we are trying to rectify in the next version. But today it is there in your Vtune tool, and you can run this application snapshot. It'll give you basically a one-page, something similar to the dashboard I'm showing, right, the screen flipping. Essentially give you a bird's eye view of, okay, so I ran it, and it also is beautiful that it doesn't require a full install of Vtune, so you could even download this as a modular thing and do it, and doesn't require an installer driver or anything. So you're able to essentially get a bird's eye view of, okay, what's my CPU, memory, and FPU, basically the vector unit utilization, floating point unit visual. And so you quickly then you give a little summary that is just essentially tells you what the interpretation of those numbers are, and then what some possible causes or things you could do to address those gaps. And essentially, this basically is telling you that you don't need to start figuring this by running full-fledged analysis within Vtune. You can figure out which analysis type to pick from, and then what specific problem you're trying to solve. And so basically, if you go back and in the workflow, I was trying to address basically triage, right? So this is what we recommend that you do. And in fact, it could even be done by almost everybody in the team. They could do a quick snapshot, and then if see issues, they can alert maybe an expert in the team who knows how to analyze using Vtune. So that's another thing that's very popular. That I think is good enough. And then with the Vtune itself, we talked about you could be focused on trying to improve your single thread performance, and then or your parallel or multi-threaded performance for overall system view for different segments like HPC and cloud, or for persistent memory storage, embedded, and also media and OpenCL. So I think that part is going to be even more going down. It's a data parallel C++ and one API. So I think I could probably skip this and then really go into the configuration workflow. So maybe a few words on the configuration workflow. So we didn't go through this before. So in this model, or in this particular abstracted or a cartoon-like workflow, right? So you're picking a particular configuration of a workload. Basically, you have a workload with certain size inputs, whatever application or a bag of applications, and then some size of the workloads. Then you are also picking a particular, maybe your first guess at what is the ideal hardware configuration. And then you essentially want to characterize using the platform profiler capability within Vtune. Well, and I'll show you next, maybe just one quick screenshot in terms of what you're able to do. And then that essentially able to tell you where are the bottlenecks in your platform. So if you're utilizing something really well, it'll light up that and show you what's the percentage of utilization of each of the resources on the hardware side, right? So those resources could be CPU cores, could be memory channels or IO channels, and also the cross-socket traffic, and also accelerators that are in the system, in the server. So there is a point where you can start to say, at some point, maybe I shouldn't be further optimizing my hardware configuration because the code itself seems like it needs to be further tuned. And that's basically your decision point. At some point, you realize that I have improved it enough, but now I see that the code doesn't have enough parallelism, let's say. Or I suspect the code doesn't have enough parallelism. That's why the utilization is low. And so rather than throttling down your CPU demand or CPU capacity in the platform that you recommend, you may want to go into the profiling workflow and figure that out. And if necessary, even go into the design workflow and further improve the parallelism. So that's why so think of them as the real life is a little bit more complex than the cartoon versions that I'm doing, but I think it's still useful to think of them this way. But if you merge these and put it, then you will see a lot more complexity in terms of how we jump from one workflow to the other, and also the complexity within a project in terms of different people involved with different pieces of the workflow. And then, as I said, in the platform profiler, what you're able to get is you were able to actually just automatically glean the topology of your compute platform, the server or client, whatever it is, and able to show you basically how many sockets do you have, what is attached to those sockets in terms of the IO devices, either be SSDs such as hard drives or NICs, and then also the DIMMs that are attached, and also what are they attached to, which memory channel, which memory controller, things like that. And then you can essentially drill down by basically looking at the topology view, and then you can drill down and then essentially say, I want to look in socket 0, and then it'll only show you even more greater detail into socket 0. And then you can even go and say, I want to look at the memory controller 0, and then that'll give you greater detail into what's the actual bandwidth read write wise on a particular channel under that memory controller. And you can also do it for the PCI devices as well. So this piece basically allows you to understand that sometimes you may be wondering why, and then it's simply that if you started with the reason why software developers need to care for it. Suppose if somebody tells you that your performance is bad, it may be that the particular system they're running on really has a poor balanced memory configuration. And that'll show up here because one of the channels will light up as being the bottleneck, and then somebody knowledgeable about how to profile a server will be able to figure that out using this tool very easily. And then the last one, and very briefly, is the correctness results. As you're doing a lot of these code changes, we also have a tool for checking for memory-related errors and also threading-related errors, and also we extended that for persistent memory-related errors, and in the future we'll be extending it for accelerated or offload correctness. Basically, there can be other errors that get introduced when you offload that are a little bit harder to catch, and so we are still exploring that space, and but you can expect we'll offer that space as well. So let me stop there by quickly, or maybe I have a couple of more things. Let me just cover this. So I promised to cover the developer experience or productivity space. So basically it's not okay to just adding more analysis capabilities. We also understand the complexity, and we are trying to figure out how to make your experience good, as well as worry about your productivity. As we make the capabilities we offer more complex, we also understand it can negatively impact your productivity unless we take a lot of care. And so that's been actually a key focus for us for the last couple of years, and it's going to continue to be a high priority. And then what are we doing? I quickly will share that there is a new feature already. We have a preview version of this in our current releases called Vtune Profiler Server, and it allows you to basically install Vtune stack on one of the servers, and then have essentially a project team may install a server in one of their network, and then be able to profile workloads running on targets within their lab or within their network. And then the project members can be able to go and browse the analysis results, similar to the same, all the full-featured UI that they see today in the Vtune desktop or application. They'll be able to do it in their browser. And so this is a mode that we enabled in almost 9 months ago as a preview feature. We are getting some good feedback and really excited about it. We'll be building on that and enhancing it further as well. And then the next one is, as I talked about, as we go through it, we're trying to organize and make it easy for you to conceptualize. Basically, Vtune has lots of analysis types. So how do it's very hard for me to keep up, or I want a quick and easy way to conceptualize what I should be doing or how to navigate this. And so we've done a couple of iterations of this in the last 2 years. And I think this one was the last year's iteration. So that is showing you how you can start to see which type of analysis to use for when you get started. Okay, I think, and then there are links here to go get more information. So in summary, Intel offers a rich and comprehensive suite of analysis capabilities to meet your needs. Not every, you don't need to know every one of those capabilities. So what I tried to do today is to basically demystify or actually make it a little bit easy that you don't need to master everything. So just understand your role and need, and figure out what things to focus on. And if that part we haven't given enough guidance, we would love to get your feedback on how we can make it easier for you to figure that out. And in general, looking for your feedback, and thank you for listening. That's all. Any questions? I think with that, I'm ready to take any questions.
Thank you, Sri. Asaf, do you have any questions in the line?
We had a few questions that we answered, you know, in the Q&A window. Maybe, Sri, you can talk a little bit about Vtune support for virtualized environments and specific operating system. What's our approach and strategy in general, and how do you see that?
So in general, we support virtualization in many. So virtualization is a complex topic. So just trying to figure out. So we do support, but I think with virtualization, you want to be clear about what we mean in terms of being able to optimize our profiles. So there are two major categories. One, we support for people that actually are at the infrastructure level. So the amount of support we have added into some of the popular open source VMMs like Zen and KVM, you would be able to get a system view and be able to understand how well your entire platform is doing, physical platform under virtualization, right? So with a rich mix of virtualized workloads running on top. So that's meant morely for people who want to see if their either virtualization is implemented well or if it is working well for a given set of loads. And then if you're a application or a specific you own only one VM, and then you are interested in profiling yours. So that's another one we support, basically one at a time. So basically, if you have a VM, so we can allow profiling one VM on a physical server, and with support that we added into the so both KVM, Zen, and also Hyper-V for Microsoft and Azure. And I think some of these are also enabled on AWS, I believe. So I think I have other experts on the panel here, and maybe they can chime in and add some links there. Essentially, if you're using any of the EC2s, I think some of the newer EC2s have this already added, certain limited amount of hardware observability is enabled in collaboration with AWS. And also Azure. We'll be happy to take more specific things. So if you have, so we understand that enabling the exact same full richness that we have on the physical hardware is not possible with virtualization, but we are also trying to figure out how to enable what makes sense or what's feasible technically. So we'll be happy to answer if you have a more specific question. Please send us offline.
Yeah, there's a few more specific questions, and we will answer them in the chat boxes.
Okay.
All right, thank you, Sri. So with that concludes this one. Thank you very much for everyone that asked questions. Again, this session